Hi, my name is Roy Hassan. I'm a Principal Analytics Specialist at Amazon Web Services. Thank you for joining me today to learn some of the best practices for modernizing on-premise big data workloads using Amazon EMR. Let's get started. You're most likely familiar with Fortnite, a massively popular game with over 250 million players globally. What's exciting is how Epic Games built a data lake on AWS using Amazon EMR and S3 to collect, store, and analyze over 125 million events per second. The solution they built allows them to gauge customer satisfaction and increase engagement, not to mention the invaluable stream of feature enhancements they can derive from this data. Organizations all over the world are becoming more data-driven. To do so, they're collecting more data than ever before from traditional data sources like relational databases, but also from many new ones such as social media, mobile devices, and IoT. These sources lead to a diverse set of data that must be managed, normalized, and joined so that everyone in the organization can analyze to extract insights. Users want the freedom to leverage their tool of choice to quickly discover available data sets and analyze them. Having this flexibility to quickly find data and extract insights opens up opportunity for users who don't have traditional analytics backgrounds, such as medical doctors, scientists, mechanical and civil engineers, factory managers, and many others, giving organizations new perspectives to help accelerate innovation. The traditional approaches to on-premise is to collect, store, and deliver insights to the business resulted in the creation of multiple different silos. Each business unit wanted to control their own data. But as data volume and user demand grew, these systems began to buckle under the increased load, making it difficult for organizations to take full advantage of their data when they needed it. Having to wait for data-frustrated users, forcing them to make copies of the data on their local machines or introduce different tools to offload certain workloads, ultimately resulting in further fragmentation and data quality issues. Moving to a distributed data lake architecture allows customers to break down these data silos, storing data in a highly scalable and durable central repository that enables ubiquitous access using the best tool for the job. It eliminates fragmentation and simplifies data quality, allowing your business to trust the data backing the analytics and machine learning predictions you generate. AWS Analytics helps organizations quickly get from data to answers by providing mature and integrated analytics services ranging from big data platforms running Apache Spark and Presto to real-time streaming with Apache Kafka and serverless Apache Flink. Getting answers quickly means spending less time building plumbing and configuring cloud analytics services to work together. AWS helps you do exactly that by giving you an easy path to build a data lake and start running diverse analytics workloads quickly. You build your data lake on top of most of the most secure cloud storage, compute, and networking infrastructure that meets the requirements of your business. Our fully integrated analytics stack has the most mature set of analytics tools, covering all the common use cases and leveraging open source and standard languages, engines, and platforms, giving you the freedom to use your data in whichever way you need. And you get the best performance, scalability, and the lowest cost for analytics right out of the box. Amazon EMR is a core component of any data lake that forms a mature foundation for organizations to become data-driven and leverage machine learning to innovate faster. EMR allows you to launch compute clusters and select from 21 different big data frameworks such as Apache Spark, Hive, Presto, HBase. And by decoupling compute and storage, unlike Hadoop on-premise, you are now able to scale each independently and pay for only what you use. This decoupling gives you the flexibility to better tailor the compute needs, enabling users and jobs to operate independently of each other. In 2019, Forrester Wave placed AWS as the leader in cloud Hadoop and Spark platforms, providing customers a mature, feature-complete, cloud-native Hadoop and Spark solution. All right, so how do we approach this modernization conversation? There are three key approaches to modernizing and migrating big data workloads to AWS. The first is lift and shift, which requires less time and effort to do, but also brings along the challenges that you had on premise that you want to leave behind. However, it's a great starting point, so we really shouldn't ignore it. Second, we can re-architect the on-premise solution into a truly modern, optimal solution that eliminates existing pain points. You may even consider moving some workloads to AWS native services, such as Amazon Redshift for data warehousing or Amazon Athena for interactive queries for data on S3. The third one is a hybrid approach that lifts and shifts an existing workloads to maintain compatibility with existing applications, but re-architects net new workloads to get the best performance and cost as you grow your business. Let's start by looking at two common deployment models. The first being persistent clusters that match what you already have on premise. You have many different users and workloads sharing the same cluster. The metadata is stored in a Hive metastore or AWS Glue data catalog, and the data is stored in S3. This model is a great target for lift and shift and a hybrid approach where customers need to run many small jobs or have interdependent jobs that can't easily be decoupled. The second deployment model uses transient clusters, spinning finely tuned clusters to meet the requirements of a particular user or a job. These clusters stay active for the duration of the job and are terminated when the job completes. Since metadata is stored in a central metastore and data is in S3, there's no duplication or concerns of any kind of data loss. Additionally, this model reduces resource contention between different users and jobs. This is ideal when re-architecting or using a hybrid approach where jobs are idempotent or users need dedicated resources for their tasks. Now, you don't have to choose between these two approaches. You can absolutely leverage them together where it makes sense. You may want to set up a persistent cluster for interactive analytics using Apache Presto that is dedicated to BI users and analysts. At the same time, you can use transient clusters to execute ETL and reporting jobs independently, configuring those clusters based on specific SLA requirements for the jobs. Next topic to consider is how to best migrate your data to Amazon S3. The beauty about S3 is that there are many different tools that already integrate with it to be able to move vast amounts of data quickly. AWS Data Sync and Storage Gateway can copy data from on-prem to S3 in real time as users create them on your local network attached storage. AWS Database Migration Service can replicate data from traditional databases to S3. And Kinesis and Kafka can allow you to create a copy of your data in S3 with little to no impact on your existing systems. When thinking about moving data, the recommended target is S3. You can start by building a disaster recovery and archival site on S3, offloading the costly on-premise storage to an inexpensive alternative with S3 for hot and warm data and Amazon Glacier for cold data. Sometimes in a lift and shift model, it may make sense to land the data in HDFS on the cluster, but even that is a rare case. So try to save time and money and just put the data in S3. Now that the data is being replicated to S3, you can think about how to best migrate your metadata, such as table schemas and partitions. When looking to lift and shift, you can create Apache Hive metastore on AWS running on an Amazon RDS with MySQL or Postgres. You can leverage AWS DMS to continuously replicate the metadata from on-premise to AWS. This allows you to keep both systems in sync during the transition. When re-architecting, you can consider using AWS Glue Data Catalog, a serverless Hive-compatible metastore as your central metadata repository to simplify your operations. We provide you with a script to help migrate your existing metadata to Glue. And additionally, since your data is already in S3, you can use the AWS Glue crawlers to automatically discover your data, extract schema information, and load it directly into the Glue data catalog. This process is automatic and painless and removes the need to synchronize catalogs. There are some cases where you have upstream application dependencies on the metadata, such as fine-grained access controls, auditing, monitoring. AWS Glue Data Catalog provides similar capabilities right out of the box. However, interfaces may be different and could require changes on your end to fully integrate. Moving on to applications. Amazon EMR provides 21 different frameworks to choose from when migrating your applications. We support version several years back, so you can be confident we have your specific version configuration to allow you to maintain application compatibility. Apache Presto is a great tool for interactive SQL, and Spark and Hive are great for ETL and data processing. Apache Flink is a popular tool for real-time streaming. For interactive development, we have serverless Jupyter notebooks inside the EMR console. To monitor your clusters, you can use the EMR console, where we extract the key metrics for ease of use, or build your own dashboards and alerting using Amazon CloudWatch. This is a really good opportunity to kind of reevaluate your jobs to see what should be kept and what can be decommissioned. You can also take this opportunity to port some key jobs from older frameworks to newer ones, more performant ones. It's like spring cleaning. So this is actually really exciting. This is something we've been working on for a while. And what you really get here is that EMR gives you the option to launch big data frameworks and configure them to really meet your workloads. But what we wanted to do was to give our customers a great experience right out of the box. To do that, we released EMR Runtime for Apache Spark, which incorporates many different under-the-hood optimizations that make your Spark jobs run 2.6 times faster compared to vanilla open source Spark. To measure the improvements, we compared EMR version 5.16 running open source Spark version 2.4 with EMR version 5.28 running the EMR runtime for Apache Spark compatible with the Spark version 2.4. I know that's a lot of numbers. We used the TPCDS benchmark queries with 3 terabyte scale and ran them on a 6-node C4 8XL EMR cluster with data sitting in S3. When you add up the execution of about 104 queries from the TPCDS test, we observed a 2.6 faster performance on EMR runtime for Spark versus EMR running vanilla open source Spark. When comparing this runtime versus other third-party managed Spark offerings running their own runtime technology, we were 1.6x faster. Compared with the third-party managed Spark offering that I was referring to, running their runtime, AWS EMR would actually run at 1/10 the cost of those 104 queries that we tested. So this means that EMR provides the best performance at the lowest cost. And finally, the EMR runtime for Spark has 100% API compatibility with the open source Spark. This means that your workloads run faster. They're saving you on compute costs without making any changes to your application. You get this completely out of the box. Now, just by running your Spark workloads on EMR, you get performance boosts without having to do anything. That is great customer obsession. It's something that we strive to do more and more. And as we continue to move forward, you'll see more of these enhancements coming down the line. All of these new performance improvements are available in the latest version of EMR. So if you're running older versions, we highly recommend upgrading. We know it's not as easy as that. So if you do need any help, let us know. We'll be happy to help you. But you do get a lot of benefits just by simply upgrading to the latest versions. We will continue to release enhancements to the EMR runtime, so keep an eye out for more really great things to come. So changing gears a little bit, I want to take a short detour to talk about Uber. So Uber, as you may already know, is a popular ride-hailing and food delivery company. They ingest and process hundreds of terabytes of data each and every day in their data lake to provide their users with curated data sets for their many use cases. They process about 120 terabytes of data in batches every 6 to 8 hours, but in reality, only a small portion of the data was actually changing. This process was too slow, difficult to roll back in case of any kind of failure or bad data, and required a lot of compute and I/O, resulting in higher costs. Trying to provide users with a fresher data led to solutions that resulted in many small files that impacted the query performance and really made it difficult to avoid duplicated data. So they sort of embarked on a way to solve this problem. Introducing Apache Hudi, Uber's solution to these challenges at massive scale, and you can now install Apache Hudi on EMR for your workloads. So what does that actually mean? It means that you can now easily insert, update, and delete records into your datasets on S3. If you tried this before, you'd recognize that this is not a simple task and requires some expertise to get right. Hudi on EMR makes it super simple to ingest change data capture, CDC, from your databases, comply with GDPR and CCPA right to be forgotten requests, and even be able to rewind the datasets to previous versions. Additionally, with Hudi, Hudi automatically optimizes your data over time so you don't end up with lots of small files impacting query performance. This is a really, really good benefit as your data lake grows and more data is stored in S3 to have a system that automatically maintains the hygienes of your data and keep it optimized at all times. The beauty with Hudi is that it's backed by the Apache Foundation and has a really good and growing community of contributors, including AWS, who run it at massive scale and for real production workloads. So this is not an experimental solution. This is something that large customers run this at production scale. At the center of the Hudi architecture is a data set. Right? This is your data set, any number of data sets. Hudi data sets can be written in two ways. The first is using a tool called the Delta Streamer. Delta Streamer can connect to S3, Hive, and Kafka to watch for files to arrive or events to be produced, and simplifies the process of applying those updates to a Hudi dataset. Datasets can also be written too using the Apache Spark data source, allowing you to interact with your datasets within existing Spark applications. For reading from your dataset, Hudi provides three different views. The incremental view allows you to query and retrieve a stream of incremental changes made to your dataset. With this view, you can see what has changed since the last update to the dataset or from a specific point in time. So allowing you to answer questions like, show me all the records that have changed since yesterday. The read optimized view is used to query the full dataset as of the last date of compaction. And is useful for use cases that require read performance and I don't need to change immediately after they are made. The real-time view allows you to query the full data set and include all the data, including the most recent changes to the data set. This view is useful when you want near real-time access to data as it changes. Okay. Kind of going back to application migration, in an earlier slide, I talked about migrating your application to those available directly on EMR. But when re-architecting, you have the option to leverage other AWS native services that may fit your use case a little better. For example, you can move interactive Impala workloads to Amazon Athena, which is a serverless and well-integrated solution for querying data that works well with your existing BI tools. You can move Hive data warehouse reporting to Amazon Redshift as a scalable and fully managed data warehouse in the cloud. For your Spark workloads, you can easily move them to Amazon EMR, taking full advantage of the performance and improvements right out of the box that I talked about before with EMR runtime for Apache Spark. For governance and fine-grained access authorization, we recommend you look at AWS Lake Formation as a serverless and free solution that is deeply integrated with the AWS Analytics services. We'll get into Lake Formation a little bit later on, so you'll see what I mean. So let's shift gears a little bit more and kind of dive a little deeper into EMR and let's understand some of the compute options that we have to work with. The basic compute concepts of EMR are a master node, which manages the cluster and can be launched in a high availability configuration and is ideal for persistent clusters. The core and task nodes are the workhorses of any operation. The main difference between them is that core nodes can include HDFS for local storage, and task nodes provide compute and memory capacity with no local HDFS storage. Task nodes are a great way to give your jobs more resources quickly to help meet tight SLAs. Amazon EC2 Spot instances are your typical EC2 instances, but at a fraction of the cost. Not all instance types are popular at every minute of the day. Because of that, we're able to give you those instances, those less popular instances, while they are in low demand at a reduced price. But once the demand for these increase, the price also increases. So for transient clusters, Spot instances are a great way to get lots of compute power for cheap, so you can complete the job quickly. But there are cases where Spot instances you've chosen become popular, which your job is running, and increases past a price point that you're willing to pay. At this point, those instances will be taken away from you. Task instance types are ideal for Spot and are simple to add and remove using EMR auto-scaling capabilities. But for those cases where Spot instance prices increase past your preferred rate and are taken away from you, EMR provides Spot instance fleets. So Spot instance fleets allow you to define up to 5 different instance types that EMR will choose from when certain instances are taken away. Use Spot instance fleets when running longer jobs or at times of day when your preferred instance types may be more popular and could be taken away while your job is still running. But rest assured, EMR is resilient and makes sure that your job continues to run as these instances come and go behind the scenes. EC2 Spot Instance Advisor can give you a live view into which instances are more popular, how much money you can save by using them, and also what is the chance they will be taken away from you. Take the time to review this dashboard to understand, based on your workload requirements, which instance types you should use during what time of the day, and you'll get the best price. So some upfront planning is required, but the cost savings are absolutely worth it. Spot and on-demand instances are how you manage compute on EMR. Knowing when to use what is not difficult, but here are some guidelines. So when you look at some of these scenarios, for long-running clusters or data warehouse type of use cases, the master node should be on demand, right? We don't want the master node to be taken away from us, because if it does, the cluster will go down. The core nodes, typically it's a mix, right? It's on demand, and maybe you can use some instance fleets. If these are jobs that require a lot of compute capacity and may run for a long time, leverage instance fleets, include some Spot instances in there. As a fallback to that, you can include an on-demand instance to say that if the Spot instances are no longer available for you, then you can switch to an on-demand instance. And then task nodes, just make them all Spot, include them in your instance fleets, and then this is how you increase capacity for your cluster. And if they get taken away from you, they can always be swapped with something else. For cost-sensitive workloads, We recommend using Spot across the board, master, core, and task nodes, because the main point here is to complete the job as quickly as possible, the lowest possible price, so you can get the most benefit by running Spot. For data critical workloads, these are workloads that have a lot of dependency on the data, and we got to make sure the data is durable and consistent. Master node and core node definitely recommend you run on-demand instances. So in case a core node gets taken away, we don't spend a lot of time moving data back and forth between HDFS nodes and risk potential loss of data. And then for task nodes, again, it just gives you added capacity, compute and memory capacity, so run those on Spot. For QA, dev, and test environments, you just use Spot. There's really no need for on-demand here. But again, depending on the workloads, but we highly recommend just use Spot for that. All right, let's also not forget that sometimes there's a need to keep data and processing on-premise. Workloads that process highly sensitive data or restricted or have some restricted data residency requirements are ideal in this case. Also, there are use cases where low latency is required, such as edge computing for high volume data that we see with autonomous vehicles and stock market trading and things like that. For those cases and more, we released AWS Outpost that places hardware on-premise running the same AWS software you know and love. It provides a hybrid offering of seamless infrastructure, cloud, and on-premise, giving you a unified operational model, which is really, really powerful. EMR is one of the first services to be supported by Outpost, and you can launch and manage clusters directly from the AWS console, the APIs, and also the CLIs that you already do on the cloud. For workloads that must stay on-premise, Outpost provides a low latency and secure solution. For those workloads that can be moved to the cloud, customers can easily use Outpost as a staging ground to accelerate migration to EMR running in their local AWS region. All right, talking a little bit about auto-scaling. So we talked a lot about using on-demand and Spot instances, but that really implies that your cluster was launched with them from the get-go. But auto-scaling allows you to increase and decrease your cluster's compute capacity in real time. We collect numerous different metrics, such as number of running jobs, memory and CPU utilization, and publish them to Amazon CloudWatch. You can then define your logic that will drive how your clusters scale up and down from that. You can also set alarms and notifications to let you know when certain conditions are met. You can use auto-scaling together with Spot instances to dynamically give jobs running on persistent and transient clusters a boost. This is a really great way to bring up capacity whenever you need it to meet SLAs. So let's shift gears and talk a little about security and what that means when migrating to EMR. Security is a very important to AWS and to our customers. Organizations have different security requirements, but we can all agree that there are basic ones that we all require. We need to have a way to authenticate users so we know who they are. We also need a way to authorize them so we can control what they are allowed to do in the system and the data that they're allowed to access. This is how we control user access. But we also need to make sure the actual data is secure, and for that, encryption in transit and at rest is typically enabled. You can manage encryption keys and certificates to give you fine-grained control over your data security. And we can't forget about the network security and isolation. That's also very, very important. Even though data is encrypted, it's important to control what traffic is allowed to enter or leave your clusters, which applications are exposed to users, and which should be disabled. Many of these guidelines and policies may already exist in your organization. It's important to capture these as you think about how to best deploy EMR before you start migrating workloads. There are multiple ways for users to access EMR and the different applications that are running on it. Most commonly, users will connect to EMR through a notebook, such as Jupyter or Zeppelin. and maybe even using the Presto client. For those users, you can leverage EMR's LDAP integration to allow users to log in with their corporate credentials or corporate identities. For power users, sometimes there's a need to SSH into the cluster to use the Spark or Hive CLI. Those users can be given EC2 key pairs that allows them to authenticate to the cluster. We don't recommend this for everyone. Make sure only the power users or those who really need this level of access can get it. Also make sure to follow the Linux security best practices to restrict users from accessing things they really shouldn't. And then use the EMR step APIs to execute your jobs on the cluster. For that, you can use IAM credentials to authenticate users and roles that are allowed to run these jobs. Kerberos. So Kerberos adds another layer of security when users and applications need to authenticate before they can actually communicate with each other. Kerberos works by using the logged in user's credentials to obtain a ticket from a central authentication service such as Microsoft Active Directory that is used to provide to prove their identity. That ticket is then used to grant access to resources within your cluster. And Kerberos is also the recommended method for application-to-application authentication. To maintain continuity for users and applications, you must first create a one-way trust between the Kerberos server running on EMR and the Kerberos server running on-premise. But we highly recommend you use Kerberos and you enable it, especially if it's already running in your on-prem environment. So authorization. So authentication only answers who you are, but we also need a way to authorize the user based on what they're allowed to do with that data. So you can define storage level authorization, which will restrict access to data at the folder or file level, both on HDFS on S3. Sometimes that's really all you need. But Spark, Hive, and Presto integrates with a Hive Metastore as well as AWS Glue Data Catalog that gives you the option to control access at a metadata layer. So this is more than just storage level. Now we're also adding controls for the metadata layer. Apache Ranger and AWS Lake Formation are two tools you can use to define those type of policies that restrict access to databases, tables, and even specific columns. When doing a lift and shift, it may be easier to use Apache Ranger, but when re-architecting or following the hybrid model, use AWS Lake Formation fine-grained access controls for user access data, for users to access data. And in both cases, use IAM to define your AWS infrastructure permissions. So I already mentioned Lake Formation a few times, but didn't really explain what it is. So let's do that now. Lake Formation is a fully managed service that provides a centralized authorization layer for data in your AWS-based data lake. It's integrated with Amazon EMR, Athena, and Redshift to give users a consistent experience as they access data from these tools. Lake Formation allows you to define access policies for users in one place using a familiar grant and revoke model. So not a new language, not new statements to learn. It's a very similar model that you know and love from the database world. Additionally, it simplifies access management by removing the need for you to define controls on the S3 buckets themselves. So when a user reads data using EMR, for example, Lake Formation will request temporary credentials to access S3 for the duration of that job. Those temporary credentials are given to EMR, not the user, eliminating any possibility of malice or even data leakage. Lake Formation also tracks in AWS CloudTrail which users access what tables, when, and from which tool, so you have a real-time audit log of user access. EMR is integrated with Lake Formation, allowing you to control access to data down to the column level. Even better, is that these business critical access control capabilities in lake formation are completely serverless and free of charge. Changing gears to encryption. So encrypting your data is actually very, very important and highly recommended. If you're not doing it, please do. It's important to do. EMR provides you with an option to read and write encrypted data from S3, either using AWS provided encryption keys or customer created keys managed in AWS Key Management Service, KMS. You can also enable encryption of local hard drives that help in protecting HDFS data, as well as when data is shuffled or offloaded from memory during processing, something that Spark and Presto tends to do a lot. And of course, data should always be encrypted in transit, and EMR gives you the option to provide your own certificates for encrypting the TLS connection. With regards to networks, it is a best practice to run workloads inside of your AWS Virtual Private Cloud or your VPC to give you proper network isolation and secure access to critical resources. When launching clusters in a VPC, make sure to launch them on private subnets so that there is no chance of unauthorized external users reaching your clusters. Use security groups to restrict inbound and outbound network traffic to your clusters and the applications running on a master node. Create service endpoints when moving data between AWS services, since reading and writing data in S3 will probably be a big part of how you use EMR. Create an S3 endpoint that moves data securely between S3 and EMR over a private network. If you need to give users access to a cluster via SSH, or to give access to authorized users, or to any applications on a master node, consider creating a job host or a NAT gateway to give access to those authorized users over a private network. And just like encryption, it's highly encouraged to employ proper security best practices when following any of the deployment models, whether it's lift and shift, re-architecting, hybrid. We have plenty of documentation and blog posts and guides online for you to refer to, and we can work with you to define the right security posture for your organization. Okay, changing to talking about monitoring and operations. So there are kind of two primary ways to monitor the health of your clusters. You can launch EMR with a service called, a tool called Ganglia that will collect and report on the health and utilization of the cluster and all the jobs running on it. However, once that cluster is terminated, you can no longer access this data. The second way is to send your metrics to Amazon CloudWatch. CloudWatch will collect and store these metrics and allow you to create visualizations, alerts, and trigger actions based on that data. It's a serverless monitoring solution that is well integrated into the rest of the AWS ecosystem and is already heavily used to trigger auto-scaling actions today in EMR. But you can also use it to trigger notifications and automatically open tickets maybe when certain thresholds are met, such as job queue is full, or the jobs that are being run are using too much CPU or too much memory and are starving other jobs when they're running. So in the EMR console, we actually decided to expose some key metrics when you select your cluster to provide you a single pane of glass that's easy to sort of monitor the progress and the health of your systems. So kind of doubling down on this single pane of glass experience, users can now access the Spark UI directly in the EMR console, making it super easy to inspect and troubleshoot jobs in real time. We went even further by collecting and storing the Apache Spark logs across your clusters for 30 days and making them available in the console through the Spark history server. So now you can troubleshoot real-time and historical jobs in one place using the tools that you already know, such as the Spark UI. This is great for operations, but it's actually a big time saver for users like data engineers, data scientists, and even analysts who primarily use notebooks to interface with EMR and need a simple place, a single way to use, to understand their jobs and troubleshoot them. So the serverless Jupyter notebooks we expose via the EMR Console actually provides progress indicators and traces to help users quickly debug their jobs. It's really all about making it easier for users of EMR to be independent and get their jobs done as quickly as possible. So switching to workflow orchestration, using AWS step functions provide you an easy way to take the systems that you've done and the workflows that you've developed in on-premise and actually migrate them and move them to a fully managed, fully automated system that allows you to continuously run these workflows on top of EMR. We've taken a step further and we've actually integrated EMR with step functions that allows you to build either cluster creations, cluster termination, and even job executions directly into step function workflows. And the beauty with step functions is that it's not just for big data. You can use it for other things as well. So now you can build pure sort of hybrid workflows that involve, maybe Lambda functions and other application systems and upstream systems, and then incorporate EMR jobs into that flow. Now that's one way to do it. It's a serverless solution. It's a great solution on AWS. But you can actually launch Uzi on top of EMR if that's a platform that you wanted to use. We do have customers who use Uzi and love it. If you're already using it on premise, you can just port those jobs very easily to EMR. And then we have other customers that like Apache Airflow. It's a great tool, has a very good community around it, and you can run Apache Airflow on a self-managed EC2 instance on AWS and connect it to EMR and be able to run your jobs there. Okay, so we talked a lot about EMR and all the capabilities around it. So just kind of in summary, when you consider migrating your on-premise Hadoop and big data workloads to Amazon EMR, remember the three approaches we discussed. Lift and shift makes it easy to quickly move workloads as is without breaking existing dependencies. It's a good starting place, and you can begin to see cost savings by utilizing the right instance types for your workloads. There's no need to over-provision capacity. You'll deal with aging hardware. Decoupling storage from compute allows you to store your data on S3 at a fraction of the cost of HDFS. You also get 11 nines of durability, high availability, disaster recovery, and intelligent tiering that automatically moves data to lower cost storage options as it gets used less. With these two modernizations alone, you'll quickly realize cost and performance benefits with little effort on your end. As you continue on this journey, evolving towards a hybrid model, you can look into which workloads can be moved off the persistent cluster and onto their own transient clusters, improving the overall experience of your users and reducing costs. So running both persistent and transient clusters, you can start taking advantage of auto-scaling and spot instances to give your workloads elasticity while controlling costs. So for example, and we talked about this before, right? Your QA, dev, and test clusters should leverage spot in majority of cases and be terminated when they are not in use. Orchestration is also important to consider when trying to improve operations and reduce costs. Running multiple workloads on transient clusters is made simple with a good orchestration system such as AWS Step Functions. So this is all a journey that you don't need to make alone. AWS big data specialists, professional services, consultants, and system integration partners will work closely with you and your team to deliver on a successful migration. So we talked about many of the great features and benefits of Amazon EMR as a target for modernizing your on-premise Hadoop environment. EMR is a very mature platform. It's built on top of cutting-edge open source frameworks and integrated into a larger ecosystem of tools and services, such as Amazon Kinesis or MSK for real-time data ingestion, Amazon Database Migration Service and Apache Hudi to manage moving relational data sets into your data lake. Amazon QuickSight for BI and visualization, as well as Amazon SageMaker for training machine learning models on fresh data in the lake. EMR is the most mature security compliance and operational capabilities with AWS Lake Formation, even governance and fine-grained access controls, making it the best choice to build a modern data lake architecture around that will serve you well into the future. And then in summary, or just to kind of conclude this, we have many different resources to help you migrate your on-prem Hadoop and big data workloads to Amazon EMR. We actually have a full detailed migration guide. If you go to our EMR/resources page online, you'll be able to download that document. It's a very complete and very robust document, so a lot of reading, but it's broken down really well into the different phases of migration and what to think about and how to plan and how to consider running these workloads on AWS. We also have migration best practices videos, kind of along the same lines of this talk today, but in video form, and you can go and listen to that and get a little bit more insight into some of these areas that I talked about today. And then lastly, we do offer a free on-site and also virtual 2-day workshop for customers who are interested in migrating their workloads to EMR. We'll sit with you, we'll do an immersion day, we'll train you on EMR and all the capabilities. We'll also deconstruct existing workloads to understand what you have, what's running, what can be migrated, and which approach should we use? Is it a lift and shift? Is it a hybrid? Do we want to re-architect? We'll also work with you to build that future state architecture. It's not just about migrating workloads from one place to the other, but it's really having that future vision to know where is your business going, what are some of the things you want to do in the future, where you want to be in the future, and helping you build that future state architecture that sets you for success. And then ultimately, at the end of that workshop, we come back with a plan and recommended next steps and how do we want to help you move to the cloud. And then you'll work with AWS professional services, or if you have an SI partner that you already work with and you have a relationship with, you can bring them to the table. We'll be happy to work with them and have them do the actual migration. And then again, just go to the aws.amazon.com/EMR/EMR-migration. Learn more about migration. If you have a question or concerns, or you want any kind of follow-up, send us an email, emr-migration-help@amazon.com. We'll gladly come and talk to you. And with that, thank you very much for your time, and we'll switch to Q&A. Thank you.